Okay, so now the panel discussion. So we've seen a lot of talks today, a lot of modeling talks, largely born out of the fact that in the open ocean, observations are so scarce that it's probably the only way to get insights at some times. And also because, as you saw today, even in the near shore, the processes are so complex and multiple, you could probably not get at them without this modeling work. So, and I know a lot of us don't do modeling, and you maybe feel shy about asking questions because you didn't understand parts of the talk. There's a lot of things I didn't understand. Please don't be shy. Now is the time for us to understand what's happening with oxygen and where these predictions are going and how robust they might be. And also you saw that if you had the impression that speakers said things that were different from each other and had different conclusions based on similar observations, I had the same feeling. So I hope that you won't be shy and you will ask this panel to deliberate on some of these questions. So, yes. Already some hands up.
Yeah, I think most people that know me know that I'm not shy even when I don't understand. So, two things I got from the modeling talks. One is that there are challenges with the models reproducing reality. But the other is many of you seem to do this time of emergence calculation. And I'm having trouble reconciling those two. If the models are that bad, how can we believe the time of emergence calculations that you're doing? And I'd just like to hear your opinions on that.
I guess I can start. I guess I wouldn't advocate that you necessarily believe as point one, but I think there's a degree to which, I think there were some subtleties in the way time of emergence was presented, and in many ways, there's different definitions of time of emergence. So, for instance, I was looking at retrospective trends and then doing this sort of fingerprint detection methodology. To me, that's a useful exercise because it provides insight into sort of the function of the system to the extent that the model provides insight into the function of the real system. And I think it does. In the CSM simulation, we have strong biases. Biases order 20%, but high pattern correlation. So it gives some indication that the mean state of the model is significantly biased, but there's something of the flavor of nature in there. And then specifically with respect to the TOE analysis in the context of, the sensitivity of the response, the sensitivity of the model to the forcing is the signal, and the sensitivity of the model, or the ability for the model to generate an interannual variability is the noise. And to the degree that sensitivity is suppressed because of mechanisms that are also suppressing interannual variability, the ratio then may or may not be very sensitive, right? So you can, it's unclear, basically, whether, but suffice it to say that I think, as an example, as an analog system, the models are useful for providing insight into how the real system is operating. So I don't put a lot of stock into a specific, time of emergence number per se from the model, but rather find that illustrative. The model dynamics are illustrative of important concepts.
Patty Matrai, Bigelow Laboratory for Ocean Sciences in beautiful Mid-Coast, Maine. My question is one about variability. So the morning, it was all about large-scale variability in large spatial and temporal scales. The talks in the afternoon were all about small-scale variability. And so the measurements tend to be more on the small scale because we can get to them there. To what extent do the larger models include, at this point, the small spatial and temporal scale? And I say this on purpose to a certain extent to jumpstart the discussion tomorrow for the Arctic, where we're just starting to get some of those measurements. And so it would be really useful to know where to put the emphasis? Thanks.
Give it a try. Thank you. Well, the small-scale variability, well, that's what we measure. And whenever we want to compare measurements with models, we have to account for the small-scale processes, implicitly or explicitly. Mostly, we have done it implicitly, but we have now run even global high-resolution models. We saw a few in the morning session. And these can reproduce a large part of the spectrum of the power of the variance of observed variability. They don't get the phases right, but that's, I think, for our process understanding, not necessary. So there we compare the statistics of the observations for local observations and these global models in those regions. And I think this gives us a pretty good constraint from local measurements for the global models. And this is important to get the statistics right. And I think that's also the major reason why we need high-resolution models, to get the statistics right, and then hopefully improve parameterizations that can then implicitly again represent the impact of variability in our current climate models that cannot usually resolve and may not need to resolve all these small-scale processes. But getting the statistics right, I think that's key. And we find that like the mean state in oxygen and the tropical oceans, it's much improved if we go to high resolution. So there these processes are relevant, even not in the variance, but even for the mean circulation. And these are not well reproduced in implicit attempts to parameterize those effects and get them implicitly into the model. So there the local observations help to improve or help to tell us where our process understanding is not good enough. And we have to be inventive to improve our process understanding. Sorry.
Okay, yeah. So I want to add that actually the work I presented kind of did, to some extent, this link between coastal ocean dynamics and global scale using a climate model. From what we saw is that you can get, with high-resolution climate models, of course, it's difficult to get the larger scale in steady state and the deep water bottoms well ventilated with high-resolution climate models. But at least in the upper ocean, we saw that you can get quite well agreement between model and observations in terms of the oxygen saturation concentration, which depends basically on temperature. What is most unknown is the apparent oxygen utilization. And I think that's a huge unknown in this link between global and coastal ocean dynamics. It can be like biogeochemical processes missing, coastal dynamics missing, but at least in oxygen saturation concentration, I think it's a good time to start making the link between this coastal and global ocean in models.
Okay, Amy Maas from Bermuda Institute of Ocean Sciences. So I'm a process studies person, so when I listen to you guys, when I hear about time of emergence, that was sort of the way I was looking at which kind of things could be useful as tracers for us to look at to improve things. So if something showed up earlier, then that might be a better measurement for us to make as we're trying to fill in all of this information. We know that information is hard to get, particularly in the open ocean, and then in the coastal systems, the time of emergence is just kind of potentially show us which processes we need to be focusing on quicker. And some of you explicitly stated which processes you thought would be valuable or which tracers you thought would be valuable. Marjorie pointed out hers, Sam gave me some. What are the other things? Okay, so particle respiration, good. Cool. What are the other things that we as a community can be doing to help you, those of us who are doing like the put a bug in a bottle kind of things?
Nitrogen fixation, I think we have to understand that. Nitrogen fixation is a net oxygen sink because the effect, in the end, you have to oxidize the nitrogen that it's fixed. And that is I think it's a major overlooked oxygen sink in the ocean. It might be balanced by denaturfication, which is then an oxygen source again. But this is something we don't understand, or I don't understand. And I don't understand the environmental controls. I don't understand how does it respond to climate change, to environmental change, to nutrient loading. And this, I think, is on the top of my wish list. Maybe it's others.
Over here, a question. This is a question I never. Ken Johnson, Mabari. A question I never thought I'd ask. But Andres, in your talk this morning, you mentioned how the observation is significantly different than the model output. How well do we trust the observations? I mean, we're looking at oxygen measurements that were done decades ago. They were collected in brass Nansen bottles. Winkler titration technologies have changed. Today they're all done with automated techniques. And I think about the ocean heat content people that spend, a lot of time thinking about biases and fall rates of XBTs and so on. Are we doing that with the oxygen data? Do we trust the data?
Yes, I trust all the oxygen measurements higher than maybe 5 to 10 micromolar, I would say. So I think they have been measured with the Winkler technique for 100 years now. And so this is, I think, pretty good. There's some, over the recent years, when new technologies come into play, there may be some corrections, but I think these are most relevant for the very low concentrations. And these are, if we look at the model data mismatches, these are details right now. And so I think they are absolutely the best data we have, much better than temperature data, where we have different measurement protocols over the decades and centuries. But oxygen, I think, is, for me as a model, as a non-expert, the data I trust most, I must say.
The data sparsity is maybe a bigger issue than the analytical uncertainty.
Bethany Jenkins, the University of Rhode Island, along with this issue of data sparsity. I'm wondering if you guys feel like there's enough flux data to model in feedbacks in terms of prolonged hypoxia and changes in things like nitrification rates and, sort of potentially augmented feedbacks by extended hypoxia and to what extent the models are dealing with that.
I think that's a great question. I personally think that the understanding how these rates will change in response to the various multiple stressors going on is something that, and parameterizing those in a way that's realistic is something is the next push for simulations to go forward, and that the models have gotten to a point now, I think, that we can start asking those kinds of process-based questions of the simulations, and that we have observations of the right order, right, to connect all this together. And I see that as what's going to happen next.
Yeah, I'll just say that I agree. I mean, in the nearshore zone especially, I think there's enough sophistication. Not that, I'm not going to call these models incredibly sophisticated, but I think there's enough there to ask those questions about feedbacks, enough of the sort of primary biogeochemical rate processes are being managed. And that gets back to the question about observations too. I mean, I think having rate measurements in general is going to help what we do a lot. We can match states, but you can get the same state because you have two different rates that are wrong, but they're compensating for one another, right? So
I always say rates and time series are always the ones I ask for.
So I'm Wei Jun Cai from University of Delaware. My question is also to the coastal hypoxia issue. So Jeremy, in your talk and later for modules, so you mentioned these different categories of hypoxia zone coastal, like retentive system, like the bay, larger bays, Chesapeake Bay, and different like river-dominated the Gulf of Mexico and East China Sea. So it seems there's one thing, you guys' modeling technique are not that greatly different, but for the bay, you keep predicting hypoxia and anoxia year after year very precisely to the outside people, but it is notoriously difficult to try to predict the hypoxia area in Gulf of Mexico or in East China Sea. But to me, the model you're using are not that greatly different. So my question is, could you speculate what is really missing in these models that seems in your, in the Bay were more physically limited, or I don't know. So if you could discuss that a little bit.
Yes.
Okay, so is this work? Is this on? Yeah, I think so. So in terms of the, I think you may be giving them the Bay too much, Chesapeake Bay too much credit to say that we get the predictions always correct. But you mean seasonal projections?
Yeah, like the area each year somewhere to come back.
So I think it's it may just be a dynamic of the system. The system is very, it's the residence time, it's the shape of the bay in the Chesapeake, it's the bathymetry, and basically the total amount of hypoxia that you'll see in a year is very closely correlated to the amount of nutrients coming in. And so I'm not sure it's that their models are so much better. I think it's just a different, maybe, like we can predict things better in the Pacific Ocean when there's an ENSO, because of the ENSO, and we can't, it's harder in the mid-Atlantic. I think it's more of a characteristic of the system and not the models. Right.
Yeah, I mean, I think it comes back to the question too that I was asked about, applying something on the shelf. It just seems like the open boundary of both those systems you talked about seems to be more complex than for a semi-enclosed estuary like Chesapeake.
Yeah, I feel compared to the study of this, I learned something.
Yeah.
Suzanne Craig, NASA Goddard. So this question goes back a little bit to a few questions back where we asked, how well do you trust the data? What I'd like the panel to perhaps edify me about is, are you able to take what is known about the uncertainty in your observations or true values and propagate that uncertainty forward in your models? Because after several decades of doing these types of measurements, we know a little bit about the distribution of the errors around them. Are you able to take that and propagate it forward in the model? And as a follow-up, I'd maybe ask as well, are the modeling approaches able to at least approximate what would happen when the models, you have a data point, for example, that is out with your training data set. What's its skill in unseen data? So that's kind of two questions there. And I speak as someone who both models and measures, so I'm interested to know how this field deals with that type of question.
Well, we try to calibrate our global models using the World Ocean Atlas data and many other nutrient, biogeochemical tracer data, oxygen data as well. And we propagate some error there, but it's mostly the statistical error, the error of representativeness. So we have grid boxes. Even the World Ocean Atlas has 1 degree grid, or we use the 1 degree grid version and then use the variance within these boxes as a measure of representativeness for our 1 degree model. And this is taken into account in the error projection, but not the error of the individual measurement, which we assume is small compared to the noise or variance within a 1 degree grid box for this example.
Because I come from the NASA ocean color world, and something that we think a lot about is we need to have some kind of degree of uncertainty, I model degree of uncertainty there. And there are methods now where we can, for example, something I'm really interested in is the kind of Bayesian framework, where we can look at the distribution of our priors along with what we know about the error and all the different flavors of error, and somehow take that forward into our model estimates or predictions, depending which one you're using.
Maybe if I can add on that, I think the main difficulty is to define the misfit. And usually we use just the RMS variance or whatever RMS error. And this is quite difficult to deal with different data types, different sampling, different length of time series, and different accuracy of the data. So like we move to new approaches and explore like Hellinger distances, where we really have the PDFs of all the data of the model output, but it's usually easy in one-dimensional or with one data type, but it becomes very complicated to deal with different dimensions, and And we still don't know what is there's no unique objective function. So what do we want? What is a good model? And nobody tells us that.
Well,
So-
that's why you run ensembles of different flavors, right?
Yes, but still, what is a good ensemble?
There are objective statistical tests to
Yes.
kind of do that in a less subjective way, and that's kind of what I'm getting at. Something that we think hard about as well. Thank you.
Yeah.
Thank you.
Hi, Alan Anadesk and Johns Hopkins. I was very interested by the contrast between Malcolm's talk and Margie's talk, and I would be interested in hearing you talk about that and getting Jeremy's comment on it, that Malcolm is able to get interannual variability of hypoxia in Chesapeake Bay with a model with basically no biology and surface equilibration with the atmosphere, and Margie gets a similar result with a model which has a lot of variability and where the surface is in fact not equilibrated with the atmosphere because there's so much ammonia oxidation. So what do you make of that?
I couldn't hear the last part. What did you say? Because of there's so much surface.
You have a lot of ammonia oxidation in your model, and it actually drives the oxygen way, way down. So I don't know what to make of the fact that these two models show the same thing. Is it in fact maybe the case that both models that your model has a process in it that tends to make the remineralization the same year to year? Are there negative feedbacks that cause that? Or is it that you have compensating processes that work in opposite directions so that the fact that that make it look like it's constant year to year?
Yeah. Well, do you want to say something? Well, you want to say something first?
Well, I can say that there are no feedbacks in my model when you just have one parameter that's constant. And so there are some fortuitous things in the model that I may be taking credit for that aren't accurate, such as I have year-to-year variability in river discharge that's doing something physically, but it's also putting in nutrients. And so I see correlations year-to-year that are positively correlated with my river discharge, even though there's no biological response. The data has a biological response, and so I'm capturing some of that. And so it's not, when I claim it's all physics, I'm probably taking too much credit for the physics. So I can't really speak to the biological feedbacks because my model has none. But there are these other compounding things that are going on anytime you compare a model to data.
I guess I would just say one of the reasons I think that we've had, and Malcolm and I have worked together and done a lot of model comparisons and all, and you know, in the Chesapeake Bay, one thing to remember is that the difference between production and respiration is only about like 5%, right? So it's really what we really need to know is the difference between, this gets back to exactly what Malcolm said, when he made his production correct, you know, more correct than the rest, then you had to change respiration, right? I mean, so it's really this difference in terms of production minus respiration. So it goes back to this many different ways to get the right concentration for lots of different reasons.
And one more thing that I'll add is that the more complicated your model is, the more you have to tune it. And so if you have one parameter, it's a lot easier to tune your model. And so I'm just tuning one parameter. And so I'll bring this up as a word of caution about models, and maybe in relation to the question about spatial scales. I recently upgraded my horizontal resolution by a factor of 10 in each direction. The number that I have to use to get hypoxia is now very different. And so I can do that very simply. I have to change one number and run it. I change that number until I get what I like. A biogeochemical model that has all of these other implicit tunings that are related to each other is much harder to do. And so that's just a word of caution.
Another example, so, you know, ours is kind of a middle complexity, but then the Bay programs, as you were mentioning, I guess, Ananda, is even more complicated with all these different phytoplankton types. When they updated the watershed model inputs, they had to completely retune that model, whereas we just went along. We didn't have to retune at all because it was less complicated again. So anyway, yeah.
So I think this follows, Victoria Coles from UMSIS, to some of this discussion. And Margie, you showed two models which are tuned in present day to equally well represent Chesapeake Bay. You couldn't determine which was better. And then you challenged them and you saw a different result. So essentially that's exactly what you're pointing at now, that these parameterizations are very sensitive. And so I guess I'm asking the panel at large, are there challenges or diagnostic frameworks, like maybe this water mass transformation framework, or standardized metrics that we can start to apply for some of the CMIP models, for example, to get at some of the different sensitivities, because these models may well be getting the right answer for the wrong reason. So Matt, I'm giving you an opportunity here too.
I guess I don't know. Oh, well okay, so it's a yeah. I can mention the hackathon, and many of you may have seen the announcement that went out. I view that more as a sort of an opportunity to collaborate on the development of metrics, in the sense that we will have the opportunity to sort of, as a community, build validation metrics and workflows collaboratively, and maybe synthesize better. But yeah, you didn't lead me to that specific comment with the question. I think Jerry, though, had something to say.
In addition to this community, the ocean biogeochemistry community, when we develop our system model, there's a diagnostic matrix for the atmosphere, the ocean physics, that sometimes we just have to compensate with each other. So some community just have to agree or just settle down with what we have. It's just impossible to get everything right.
Okay, I want to thank everyone for their enthusiasm for this session and thank our speakers again.